I figured out half of the problems. I'm not quite sure.
Okay. How should it be done?
Um, I'm still not sure how should it be done, but I figured out what went wrong with the minus part one. So the problem here is that what it's end up being is that what is the effect of how much of the like how much did A spend more than B, and that part is how that affects the vote. Then basically it should not be zero because expectedly as it increase and as it increase, it should probably increase the vote as well. So that's why the test here show that we
have to
can
include them all, right?
yeah.
So that if you take the minus, it's the first thing is that the impact of the expenditure by A itself, and then the opposite of the impact of B of the expenditure by B, right? So
Yes.
actually they are working as if B is tending to demonize himself.
Yes.
Right? If you take the minus, right? Okay. If you take the minus, so let's say here we would expect the impact of the expenditure of A on A's voting is positive. The expenditure of B on A's voting is negative. And now if you take them the subtraction, you are just simply adding the two impacts together as if B is now foolish enough to spend on demonizing himself, right? So that cannot be a minus. But a plus is not a plus is not a satisfactory configuration. Now, I give time to you one more night to think. And tomorrow you can present me with. Now you have to think of it this way. Firstly, you need to show somehow that the impact of A on A and then the impact of the other. So there must be one more term. So I will not say too much. There must be one more term to isolate the impact of the expenditure of A on A first. Yeah. Okay, good. So we leave the problem sets here. I think going forward, more or less the questions will be are more or less the same. And I think if you spend the time on running the questions, answering the questions, you will uh, improve your understanding of our discussion a lot. So, for example, there is an interesting problem number 6. The following analysis was obtained using data in MIP 93, which contains school level pass rates as a percentage on the 10th grade math test. The variable expend is expenditure per student in dollars, and math 10 is the pass rate on the exam. The following simple regression relates math 10 to log expenditure. Interpret the coefficient on log expend is again the same, right? So we'll be do it. In particular, if expend increases by 10%, what is the estimated? Come on. Now, question 2 is, does the small r square? I need to record the lecture. Do I need to record it at all? I mean, that's maybe the first relevant question, right? Should so you know, so we visual lecturers are seeing some problem. We visual lecturers are seeing some problem that we create ourselves, and this is very serious. So we treat our students as our sons and daughters, to provide them with everything that they need. And when the visiting lecturers and the flying lecturers were asked the same thing, they were very surprised and annoyed. Why do VQ students ask so much? Why do they need the video recordings and so on? So, hello, Mr. Minh Chung, you are back. Okay, I was mentioning you in the morning, but yeah. So let's say I understand that in Germany the lecturers do not record their videos, right? No, right? And I understood from the most recent lecture the flying team today this year are indicating that they were not allowed to record the lecture at all. The university account that they were given disable the recording function. So VU students will not have the recording of the lectures either. So let's say, yeah, but for the sake of being efficient, I will keep recording it. Sometimes you don't have, to be honest, you may not have enough time to read to watch them all. But if for some reason you miss a point or for something, I need you to recall it. Okay. Ladies and gentlemen, could you please forgive me? I have to restart my computer. I cannot make the recording at all. I don't know why. This is annoying. Now I have to restart the meeting again. Yeah. So please bear with me. Okay, ladies and gentlemen, it seems like the problem comes from so I'm sorry for keeping you guys waiting. So now the thing I can assure is that the my lecture will be recorded, but your contribution will not. I don't know why. It's just simply refuse to provide the access to the system audio, even though I have restarted my computer once. So let's say it will not have a big impact. So I will try not to ask you in the afternoon. Many are in a lot of agreement with that policy. But let's see. Let's see. Okay. Um, so let us go on with session number 3. And I think it will not be a too big topic now because we already touched the issue here and there. So now we will. All right. Okay. Let us go on with our discussion so far. So if the assumptions of the OLS models are all satisfied, our results are perfect, and our interpretation are valid. We have found ways to better our world, and congratulations. The problem is when the assumptions are not met, then our interpretations are wrong. And if we invest based on those interpretations, we are destined to make a big loss, right? So yeah, we have to make sure that our interpretations are valid, and with that we can make sensible decisions based on what we have found. I myself am very confident with my IT skills. But I have to say, like, as everyone starts using the online lecturing, the problem seems to be a little bit more difficult to deal with. But let's say we will keep focus on our lecture. So in case that we don't have our recordings today, I don't know what kind of recording we will get, because it keeps signaling something like the lecture on Monday. So if that is not the case, you have the video recorded some years back, and the informations are more or less the same, except that in those videos, the content might be more advanced. Now, so we have 6 assumptions of the OLS model. So we have, they call it, another name for those assumptions is the so-called classical regression model. Okay, so it should be, the first one is linearity, right? The second one is for rank. The third one is exogeneity. The fourth one is spherical disturbance. This spherical disturbance assumption involves 2 assumptions. One is the so-called homoscedasticity. And then you would have the non-autocorrelation. Okay. Then we have number 5. That is the data generating. Process. And then step number 6, that is epsilon. Square. Now, what I'm writing here is, when I write epsilon, I mean it is a vector. And if it is a vector, then the variance covariance matrix is an n by n matrix. If I write EI, then in that case, I don't need the I here. Yeah, I don't need the I here. So we have 6 assumptions. And it is 6 assumptions. Now, the first one is linearity. What happened? What happened if the variables are the relationship in practice or in reality is not linear? So let us come back to our example that we did in session 1. Yeah, in session 1, we did this. In session 1, we did this. In session 1, we did this. So we created a series of artificial relationships. What do we mean by artificial? That is, we created they themselves, ourselves, and we know the true relationship. So, for example, in this equation, we know that x5, x4 is equal to x2 times x3 squared. Okay, so in this case, we know x4 is equal to x2 times x3 squared, and in the equation of y2, actually the true relationship is y2 is equal to 3 plus 2 times x1 plus 3 times x2 plus 4 times x3 plus 5 times x2 times x3 squared. So this is a nonlinear term. This is a nonlinear term. If we, and after that, when we run the regression, if we regress x1 on x2 and x3, ladies and gentlemen, now, so if we regress x2 on x1, y2 on x2, x1, x3, this is the regression. Okay. So y2 depends on x1, that is true. x2, that is true. x3, that is true. It also depends on this nonlinear term. I'm sorry. It also depends on this nonlinear term. The nonlinear term is nothing more than the term 5 times x2 plus times x3 to the power 2. So this is by construction, y2 is the result here. Y2 is the result of the interaction between the disturbance term x2, x1, x2, and x3. Of course, x2 and x3 also appear in this nonlinear term. So if we are not aware of this fact, and we just run the regression, regress y on x1, x2, and x3. Yeah, y on x1 and x2 and x3. We would get something that is hugely different from the true relationship. You may see it here. Yeah, nothing is. There even the slightest resemblance to the true relationship that we have created. This is very problematic. So, however, as long as you bring the linear term into the model, that linear term is x4. If you do the regression of y2 on x1, x2, and x4, you may see, this is something I have done, and I come back here, you may see that the results are very precise. Very precise. So when the model is not linear and we assume them to be linear, the probability that we get it wrong, the coefficients are totally different is there. So we have to correct for that by looking at our slides here. So the inference we have made so far relies on the assumption that the dependent variable is linearly dependent on the regressors. Regressor here is another name for the explanatory variable. So we have the Ramsey's test, a reset test. To test this assumption, I include a non-linear term into the model. So basically, the Ramsey test is very simple. If you doubt that the model is not linear, then you run the regression, you get the predicted value, you square it, take it to the power 3 and power 4, and then you include them all into the original regression. Then you test for the null hypothesis that gamma 1, gamma 2, and gamma 3 are simultaneously 0. If that is the case, if they are all 0, the model does not show any nonlinearity problem. If the test is rejected, then we have to reconsider the model that we are considering. Under the null hypothesis, the original model is correctly specified. The coefficients on the additional terms are 0, and the F statistics resulting from restricting those coefficients to 0 is not significant. If the null hypothesis is rejected, researchers must consider augmenting the model specification. Okay, so let us have a look at the examples. So in this example, we come back to our recursion using the Vietnam's Living Standard Measurement Survey again. Yeah. So firstly, we run the regression. This is our regression, and we want to test. The test is very simple. You just, after running the regression, if you put is that over test, then you would get the result. This is what you would get. Yeah, and at 0, the model has no omitted value. So most of the time, the omitted value are the nonlinear terms that make the model and that make the relationship nonlinear. And what is our conclusion with this model, ladies and gentlemen? So basically the sense is you test simultaneously the coefficient of y hat square, y hat to the power 3, and y hat to the power 4. And what is our conclusion here? If the result is like this one, if you read the statement of the software, how should we interpret the answer? Let's ask Đỗ Long Duy. Hello, Long Duy.
Yes,
Long
I'm here.
Duy.
I'm here. Yes.
Okay. So in the morning, I miss you a lot. I invited you twice, but maybe your mic was broken. So now it's very nice that we are together. Now, like my Long Duy, how should I interpret this test result? Hello.
Yes. I'm sorry.
You don't know how to interpret it.
Yeah.
That's too bad. So if this is the p-value, Long Duy, so what do you remember from interpreting the p-value? So if you reject the null, what is the probability that you will make a mistake?
The when I reject the node,
What is the probability that I will make a mistake?
is that 0.007? Is that the probability?
Is that true? You don't know. Come on, Lamzi. This is not bad. This is too bad. Now, you will listen to your peers and then see how they make the interpretation, okay?
Okay, yeah.
Yeah. Now I will try to invite someone from this one. Now, Mr. Nguyễn Huy Thắng. Hello, Huy Thắng.
Hello, can you hear me?
I can hear you well. So what is the interpretation of this test result?
The probability that you are wrong when you reject hypothesis is 0.007.
Okay, so should we reject the null at 1% level?
We at 1% level, I think that we should reject the no.
Okay, so let's say you sound very reluctant, but actually this one is smaller than 0.01, right?
Yes.
And if it is smaller, it means that if you reject the null, the probability of making a mistake is about 0.7 thousandths.
Yes,
right?
and your your
0.75.
tolerance level is 1%. Is that true? And then,
Okay, yeah. If you the margin of error is even smaller than 1%. So if I accept 1%, I'm safe now, right?
yes.
Okay. Now, ladies and gentlemen, now we go on with do the test manually. Okay. Now, doing the test in the format that has been in the built-in function is a handy thing, but doing the test manually will provide you with the sense of the model, so you can understand better, right? Now, so the first thing is we make some predicted values. Now, if I put the I run the command predict E residual, what do I get? And this is a lazy way of writing it. If I even type res, the model would understand that I need the residual. If I type R, it also understands that I need the residual. If I type residual, it also give me the residual, right? So it's a very handy and subcommand that could be abbreviated in different ways. So I put predict E residual. What do I get? I would get the error term, right? If I run the command predict y hat xb, I would get the residual. I'm sorry, the predicted value. Now, so what do I get if I type y hat residual? What do I get if I type y hat residual? So what is stored in y hat? Miss Trần Thị Thiên Trúc ạ. Hello Thiên Trúc.
Yes, sir. Yes, sir.
Hello Thiên Trúc.
Can you hear
so
me?
if I can hear you, yeah, I can hear you very well. So what do I get if I run the command predict y hat, comma residual?
I think you're gonna get error term.
The error term, right? So it doesn't matter what name you put here. If you put RM, if you put VGU, you would get a variable with the name VGU. Okay, it doesn't matter which what name you put. What's important is the subcommand at the end that will tell Stata what quantity to estimate, right? Okay. Now, Miss Thiên Chúc, so looking at the Ramsey's reset test, the mechanism of the test is that you doubt that some of the explanatory variables. Now, Mr. Longji, could you please follow me?
Yes, I'm following you.
Okay, good. Now, the mechanism behind is when you feel. Now, Minh Giang, just listen to me and you will see what we need to do. When you feel, when you want to check if your models are correctly specified, that is, you doubt that you have missed out some nonlinear terms or some other variables that make it nonlinear, then you will create 3 new variables, which are the square, the cube, and the power fourth of the dependent variable. You include them as the new explanatory variable, and you test for their significance level. You test simultaneously that these variables are relevant. Now, so I follow this manually. First, I predict. I generate the y hat square equal to y hat square, y hat cube, and y hat quad. And I run this regression, right? Now, my question is, if I want to test y hat square, y hat cube, and y hat quad, what should I do? That's the question. What should I do? And I want to continue with Mr. Phan Huy Thắng. What should I type in data? Yeah. What should I type here?
I think that you should type the predict.
I want to test. I can't type predict if I want to test. Now I want to
So
test
you
y hat square. Pardon?
You type test y hat square.
This is the one, yeah?
Yes.
Oh, it's already there. I'm sorry. I should have known that. But that's fine. Yeah. If I run that, I will get the test that will provide me with more or less the same answer. Do you see that is 5.63 here? And when you use the built-in function, it is 5.64. So there might be a little bit difference. The reason is because of the rounding up during the computation process. Yeah. So they are mildly different. Just 5.64 and this is 5.63. Yes, just some minor differences. Okay. Now, Minh Giang's question is, yeah, so what do we do? Wonder what the above H0 is rejected. Is it also the case violate the full rank assumption or is it just linearity? Now, Minh Giang, this is just linearity, right? So the question, the thing is, if it violates the full rank condition, you will not be able to estimate the model, the coefficient. So if you look at the example down here that we have had, you may see that y2 is regress on x1, x2, and x3. x1, x2, and x3 are linearly independent. Is that right, Minh Giang? So there is no violation of the full rank assumption. Yeah, but this is not a violation of the full rank assumption. So when you do not bring the model into consideration, your specification is not really precise, but the matrix of variables being in the explanatory set is still linearly independent. They still allow you to estimate. It's just that the wrong estimate. Okay, the wrong estimate. Now, so this is different from the violation of the full rank. We will talk about a full rank going forward. But you at least you understand what the Ramsey recess test is, Minh Giang. It is just the test of whether there is a true linear relationship first. Okay? Even if when there is a linear relationship, if the variables are not, the columns of the variables are not a full rank, you cannot estimate at all. So this comes to the second assumption. Now, so what is the implication of this one? If after running the regression analysis, let's say we come back to our discussion here, and if you test, the conclusion is that you have to reject the null. And if you reject the null, it means that the assumption of no non-linearity is violated. So you have to think of model it again. You have to maybe you have to look at this is a sense of modeling. So you have to look at the data. You have to look at the other variables. So in this case, I just suggest now, ladies and gentlemen, I just suggest one way. One way of fixing it is to check the data. So the data here is yearly pay. And if you make a summary, you may see that some people have very low. So if you do the summary, you may see that some people have exceptionally low level of income per year. This is in thousands. So some people may have only about 1% of the bottom of the distribution has the income of only 1.3, almost 1.4 million per year. That's quite small. And some people have the income of about 106 million per year. This is the data in 2010. So in this way, it might be the case that some of the variables about reported income were miscoded. For example, some people say, how much do you earn? And they say 13 million, but the surveyor may for some reason put it 1.3 million. That is the possibility of errors in the data. So what the suggestion that I included here is, okay, firstly, I will sort the data, and I identify the 0.5 percentile and the 99.5 percentile. That is the idea. I rank the data from the smallest. This is the idea. I rank the data from the smallest to the largest. And this is the first 0.5%. And this is the top 0.5%. I will delete any variable that is larger than 0.5 and any variable that is smaller than 0.5. Meaning that of the 7,542 observations, now I will probably drop 35 smallest and 35 largest observations. Yeah, I will drop the smallest one and the largest one just to remove them. And when we do this, we are dealing with the so-called outlier. Deal with the outlier. Outlier. Yeah. So if I do that, ladies and gentlemen, let's see. In Stata, the command underscore percentile, you give next the variable name and then you give the percentile. Stata will give you, we will calculate for you. The calculation is stored in a memory. So if you type drop if year is smaller than 0 RR1, after running the regression, if you type display RR1, you will have the number. So about 0.5% of the people have the income of 0.5% of the surveyed individual has the income of 950,000 or less per year. That is very small amount back in 2010. Yeah. Or if you type display RR2, this is what you would get. So about 0.5% of the people having the income of 132,000 million per year. So if you drop them, everything below that number will be dropped. So in total, 74 observations were deleted. Okay, 74 observations were deleted. Now, if you run the regression again, it will provide you with the result that looks more or less the same. And then if you run the nonlinear test, you will see that so what is our conclusion now after deleting the outliers? Seem to be okay, right? To be okay. So this is a way of a sense of empirical modeling, ladies and gentlemen. So when you have to as a scientist, when you are a student, a young scientist, the lecturers would ask you, have you tested the non-linearity? Have you tested for endogeneity? Have you tested for homoscedasticity? When you are a real researcher, they don't ask you that. They just reject your paper. So it is, if you submit a paper, to a journal and you don't do this thing, and if they doubt it, they will suggest your paper to be rejected. Yeah, and these are very basic, fundamental techniques and knowledge that econometricians have to understand and have to carry out and I have to follow to make sure that their scientific findings are reliable. Yeah, are reliable. Good. Now we talk about the second assumption, that is multicollinearity. As discussed in session 2, the OLS model can only be estimated if the matrix of explanatory variables has 4-column rank. I understand. I understand what Minh Giang means. Hey, Minh Giang, in the we are going to the full rank discussion, but in the full rank discussion, because of the multicollinearity, they omit that variable. So in the set of 10 variables, one of them is a collinear or the combination of the others. Theta will drop that variable. The omitted there is theta omit the variable so that it could invert the matrix X prime X. This is two different. In the nonlinear case, the omitted variable is because our students have not incorporated enough explanatory variables into the model. Not because that they deliberately drop it out. Okay? Okay, good. Now, so I will talk about that and I will explain to you. Now it is 2 o'clock and we started 15 minutes late today. But anyway, I have an interesting question for you. Yeah. As discussed in session 2, the OLS model can only be estimated if the matrix of explanatory variables has 4-column rank. If one of the column of X is a perfect linear combination of the remaining columns, the matrix X prime X to the minus 1 does not exist, and the parameters cannot be estimated. In practice, a more common problem facing modelers is multicollinearity. That is, when one of the various columns of X can almost, but not perfectly, be a linear combination of the other columns. Now, so I will explain to you why that is a problem. Let X be a matrix of a constant and K minus 1 explanatory variable of a constant and K minus 1 explanatory variable. Xk be the kth variable and X with the subscript K be the matrix X that excluding the Xk variable. Is that okay with you? So please read it. Okay. Now please read the statement again. Let X be a matrix of the explanatory variable, and Xk is that matrix of explanatory variable with the Xk removed. So my question is, how many column is there in the Xk in this one? How many column is there in this one? Miss Đỗ Khánh Linh, hello Khánh Linh.
Hello.
Hello. So how many columns are there in the Xk?
Hello, can you hear me?
I can hear you.
And can you repeat the question? My internet is not good.
Okay. So my question to Khánh Linh, in the statement that we are discussing here, what is the number of columns in Xk? Xk is here.
The number of column. Wait a minute. The number of column is K minus 1.
That's it. That's correct. I am opening my participation list. So as I invited people, I would give credit. Okay, I give Khánh Linh a plus and half a minus.
No.
I haven't finished my statement yet. So I give you your plus for the right answer, and then half a minus for not really following my question. But anyway,
No, because my
0.5.
laptop is broken. I'm using my phone.
Okay.
I'm sorry.
Okay. So 0.5 would be rounded up to be a 1. Okay. So you still get a plus, but you have to follow me. Yeah. Okay. So did you get me, Khánh Linh? Okay. So in
Hello?
the end,
Yes.
okay, in the end, I still give you a plus, but that is it is always fun to look at your credit points. Yeah. So if you look quickly, you may see all of you got the credits already. I'm now giving the priority to the ones who do not have a lot of credit yet. So the kth element, the kth diagonal element of the matrix x prime x to the minus 1 is written as xk prime m k xk to the minus 1. And it is equal to xk prime xk minus this one. If you factor out xk minus xk, inside you would have 1 minus xk times this one. Yeah. And what is the name of the matrix here? What is this name? This matrix. I want to invite Phạm Hà Minh Tâm. Hello, Minh Tâm. Did you answer something in the morning, Minh Tâm?
Yes, I did.
I think we did have a conversation in the morning, right?
Yes.
Okay. So I put a question mark there. Hey, Minh Tâm, what is the name of this matrix? Huy Thắng, I already gave you a plus. Sorry. I think so. Nguyễn Huy Thắng. See? Okay. Now I already made it. Now, Minh Tâm, could you please give me name this matrix, and then I am eager to give you some pluses.
PX.
P.
PX.
PX. Is that right?
Yeah. Yes.
No. It is something else. What is different between x and xk?
I don't know.
You don't know. It is x prime xk prime p xk, right? Now I think to be precise, in my right hand writing, it should be xk prime p xk xk. Is that right, Minh Tâm?
Yes.
Yeah, this is the projection matrix on the set of
Right.
k minus variable, removing the variable xk, right? No. So what do I get if I write px k xk? What is this? What is this quantity, Minh Tâm? What is this quantity, Minh Tâm? I always ask Mintam difficult questions, right? Hello, Mintam, can you guess what is it? No? Then let me ask someone else. Hello, Dan Thanh. Hello, Dan Thanh. Are you, have you fully recovered? Maybe she just opened the computer to record it. That's fine. Yeah, I have no problem with that. I would like to ask, hello, Minh Nguyên, you were so tired were quiet these days.
Hello, can you hear me? Hello, can you hear me?
Hello, Minh Nguyên, how are you?
I'm fine. I'm
Yeah.
tired.
Can you say it louder, please?
Hello, can you hear me?
Yeah, I can hear you now. It's quite okay. Can you please speak? What is the quantity pxk times xk in this case?
Let me see.
P x k times x. What is this quantity?
I think it's K.
Can't hear you.
I think it's K.
Hey, you think it is?
It's K.
Is it K? What? What is it?
Oh, sorry, I can't hear you clearly. Do you say anything?
Oh, you can't hear me. Okay, now my question to you is, what is the quantity pxk times xk as I have written on the screen? You may need some more time to think about it.
Yes, I think so. Maybe X.
Okay,
I think it's K.
it's K? Xk?
Yes.
I mean this one?
Yes.
No. Now you have to understand how we come up with the xk. Now you have to think of it here. Let x be a matrix of a constant and k minus one explanatory variable, right? Then we remove the xk is the matrix x with the k variable removed. And as Đỗ Khánh Linh said, it's now is short of one column in comparison with the original matrix. Okay, so now my question is, what is the quantity pxk times xk? Right, that's my question. I may ask someone else. Lê Hoàng Tuấn.
Yes, I'm here.
Tuấn,
Can
are
you
you
hear me?
there? Okay. What do you think is the quantity of pxk times xk?
I think it is xk hat.
What is xk hat?
Is the predicted value of xk.
How can I predict the value of xk?
So basically, pxk is a matrix without xk, right? So if we wanted to predict something else, in this case, xk is not in the plane. So if we project you borrowing the matrix xk, which means without the x small xk, then somehow we will be able to predict the small xk.
How
Is
can what do you mean by that somehow?
Then delete somehow.
Somehow is not a science, not a scientific way of expressing things. How do you mean by that somehow?
Somehow, let's just delete it. We will predict xk.
By what way? Can you say it? Can you say it in a clearer way? I think you are going in the right direction.
Okay. So it's like
Taking what to regress on what?
yes, thank you. Yes, that is, yeah. So we regress. So we regress x small xk on the matrix xk, and then we will have the predicted value of xk. Xk small xk. Yeah.
That's what you mean, right?
Yeah,
That's what you mean by xk hat, right?
Yeah.
Yeah, okay. Do you all agree? It is nothing more than pxy, you know? It is similar to something like pxy. But in this case, the matrix x is different. You just take one column of x and regress that column on the rest and get a predicted value, right? Get a predicted value. Is that right, Hoàng Tuấn?
Yes.
Okay, that's a very nice answer. Yeah, that's a nice answer. Good.
Thank you very much.
Okay. Okay, that's the right answer. So now I want to again. I want to quiz you guys again. What is this? Is a very quick answer. As long as I write it down, I invite a name. That person must answer immediately. No 30 seconds for thinking. Okay. So what is the quantity y prime y hat prime y hat on y, let's say y hat prime m1 y hat over y prime m1 y. What is this quantity, ladies and gentlemen? Nguyễn Hoàng Hải ạ.
Can you hear me?
I can hear you. What is the name of this one, Hoàng Hải?
That must be the R square.
The R square, right? R square. Now, later on, I may, I may ask you to prove something like m x mxk is equal to mx. Px pxk is equal to px. If you times those matrices together, they will be the same. Yeah. Now, so if you look carefully at this expression here, you may notice that it is equal to 1 minus xk hat prime xk hat over x k prime xk. Xk prime xk. K prime xk. okay, over xk prime xk. And in the regression, and it could be shown that the quantity inside here could be rewritten as this one. So it will be equal to 1 over 1 minus r square times skk. That r square here, the r square here is the r square from the regression. This is the r square from regressing. Xk on xk. Now, ladies and gentlemen, looking at this expression, if xk, what happened to this quantity? If xk is highly correlated with xk, then the r square will be close to which number? If that is the case, then the r square will be close to. Now, if this is the case, then the r square will be close to. I will ask someone. I think I am impressed with a name that has been silent for this stage. Now, Trần Ngọc Đan Thảo ạ. Hello Đan Thảo.
Yes, I'm here.
Hello Đan Thảo. So if xk is highly correlated with the matrix xk, then the r square and this r square will be close to. If they are highly correlated, meaning that most of the variation in xk could be explained by the matrix xk. So it will be close to.
Maybe 0.
Hello Đan Thảo.
Hello, I think it's maybe 0.
0. Now, do you all agree? Okay, thank you, Đan Thảo. Let me ask. Nguyễn Thảo Ngọc. Hello Thảo Ngọc, can you hear me?
Yes, I can hear you.
Okay, so can you answer my question?
I'm sorry, I'm
question is
still
here.
thinking.
You still need some time to think, right?
Mm.
Now, Miss Phan Thùy Linh. Hello Thùy Linh.
Yes.
Yeah. So what do you think this r square k dot will be close to?
I think 1.
It's 1. Why is that 1? Because if they are highly correlated, then all of the variation in xk could be explained by the matrix xk here, right? Is that correct?
Yeah.
It will be close to 1. When it is close to 1, 1 minus something close to 1 will be, this one will be close to 0. 1 divided by something that is close to 0, the whole thing will be close to infinity. So the error term will be the standard error. If that is the case, the standard error, if this is the case, now, if xk is highly correlated, right? No. With xk, right? Then the standard of bk is, standard error of bk is sigma square skk. Okay, skk is skk is 1 over 1 minus r k dot okay, skk. So this one will be is very large. If it is very large, then the confidence interval of the confidence interval of bk will be beta k will be beta k larger than minus bk plus I'm sorry, by bk minus the standard error okay minus the standard error of bk smaller than bk plus the standard error of bk, which will be, this one will be close to in minus infinity, and this one will be close to infinity. So in that way, the confidence interval of beta k is large, and our estimate is not precise. So for example, we are interested in explaining the impact of VGU, of having a degree at VGU on lifetime earning. And the coefficient is, let's say, 0.5. That is to say, if you have a VGU degree, you will have 50% higher wages and salary. But the confidence interval is from minus 20 to 35. Minus 20, I'm sorry, to 9 to 70. Yeah, minus 20 to 70, let's say, or to 90 actually, right? To 80. So that is the way you say Either having, on average, having a VU degree will earn you 50% higher wages, but at the lowest level, it could cost you 20%. So in between, there is a zero. And you do not really know if your coefficient is significantly different from zero or not. You cannot make a conclusion. Yeah, you cannot make a conclusion. So for that reason, when variables are highly correlated, you may consider to drop some variables. So when one variable is highly correlated with the other variables, the information that the correlated variables brings in the model may be minimal. So unless there is good theory to include highly correlated variables into the model, you may consider drop some of them. And now it comes to Ming Zhang's question. I know Ming Zhang is struggling with keeping her eyelids away from each other, but but this is the negative impact of having your video open. But let's say, don't worry, Ming Zhang, I'm just telling the truth. The others, they turn off their camera and they cannot say anything. So I still appreciate. I was still dozing off during my classes back there at the Diplomacy Academy. So don't worry. The thing is, normally in data, when the variable is highly correlated with the other variables, then data will automatically drop that variable from the analysis. Okay, Minh Giang? Good, good. Okay, so that is what I have for the now. So in data, they will calculate for you the variable with the name VIF. VIF. The name for this quantity is the VIF. And there is the abbreviation of the word variance inflation factor. Variance inflation factor. So if a variable is highly correlated with other variables, if a variable is highly correlated with other variables, then the VIF is very high. If the variable is not that strongly correlated with other variables, the VIF is low. Yeah. So basically in data, it has been demonstrated here. VIF computation, if you run the regression and you type is that VIF, data will give you the list of the variance inflation factor. Everything higher than 20 should raise your eyebrow. Now the rule of thumb is 20. Everything higher than 20 should be a sign of warning. Okay, sign of warning. Now Bùi Minh Trung had a correct answer. He typed into the chat box privately. But yeah, I remember that. I give you a put of a plus. I will remember that. But No, I cannot say half a plus because it will be rounded up following the previous practice. So I recognize that. I know that you got the right answer right from the beginning. But I was asking someone else, and I would like to thank you for not to revealing it. Okay. So now we have a break. We have a break now. We will come back in let's say it's 2:30 now. We will come back at a quarter to 3 sharp. A quarter to 3 sharp. That means that you will have 12 minutes break. Okay. Thank you. Okay, welcome back, ladies and gentlemen. Hello. Hello, hello, hello. Okay. So, welcome back. Okay. So, in before the break, I was saying like if you want to check the collinearity problem of your empirical model, after running the regression, you just need to type VIS stat VIF, and you would get the result. Yes, and the solution is that if one variable is highly correlated with the others, you may need to consider dropping it. Why? Because the information, now mathematically, it will make the variance of the variable very large. It will inflate, you know, inflation, something very scary. It will inflate the variance of the estimated coefficient, giving you a nonsense confidence interval. That is a confidence interval that is so large, containing the zero value. And you cannot say whether your estimated coefficient is truly different from zero. Yeah, truly different from zero. So in practice, people often follow the so-called general to specific approach to select the most significant variables. However, again, we have to strike a balance here. We cannot simply select the variables that are significant and omit all other variables that are not significant. So that there is a sense of, let's say, modeling is like an art. You must consider which variable to bring in and which variable not to bring in. For example, in our example here, the variable h and h squares are very problematic. They are highly correlated. Why? Because if you type correlate h and h2, you get something of 0.98. Is it a contradiction here? H and h squares are definitely, ladies and gentlemen, h and h squares are definitely nonlinear. How could it be that linearly dependent? That is because when you have two segments of two curves, for example, if you have this is x, right? This is h, and you have h square, but the function depends on other variables. So after some part, the part that you're interested in, this is something like this one. Let's say. In that way, they are almost linear. Yeah, they are almost linear. So when that is the case, or you just think of it in this way. This is h is here. The relationship is nonlinear, but over the space, this part and this part are highly correlated. Yeah, this part are highly correlated because you do not consider the relationship over the entire range of the variable age. You only focus on the people who are working. So in that case, even though they are nonlinear variables, they are highly correlated because you only look at a specific segment of the data. In that case, do we need to include h square? The answer is yes, because theory and empirical relevance indicate that our wages and salary cannot keep growing. I know that you guys may live up to 150 years, but your wages and salary may somehow, when you are 100 years old, it will start to level out. It cannot grow higher. Right? So Minh Giang is again very fresh after hearing that she will live up to 150 years. But congratulations, your generation may enjoy that. Don't know, lucky or burden. I don't know. If you live for too long, maybe you have to think of a lot of things, right? Okay. So the rule of thumb is include as many variables as possible as control variable, and then remove some variables that you think that are not important and they are highly correlated. Yeah. So there is not a very specific rule on how to proceed, but how to proceed I have include in the slide. So now we will talk about heteroscedasticity and before going to the problem of endogeneity. So heteroscedasticity. Actually, you look at the variation of the variable food expenditure here. The variation here, you may see that if you draw a normal curve, it will be something like that. But the variation here is like this one. So clearly you see that the variation of disposable income, of food expenditure in relationship with disposable income is not constant. So when sigma 1 square is not sigma 2 square, is not sigma n square, then the variance covariance matrix x prime sigma square x prime x. Now I was want to say x prime x to the minus 1 x prime epsilon prime x prime x to the minus 1. This one is totally different from sigma square times x prime x to the minus 1. And if this is not the case, our variance covariance matrix will not be written like this way. Yeah, this way. And it will be more complicated. Okay, so what is the implication? What is the implication of this violation? The implication is that the variance covariance matrix cannot be written in this format. However, the expectation of B of your estimate given x is equal to beta times x prime x to the minus 1 x prime epsilon given x, and it is still equal to beta. So the implication here is the variance covariance matrix will be more complicated, but your estimate is still valid. It's just that your estimate is still okay, but it's just that the confidence interval is no longer precise because your variance covariance matrix is now no longer this one. It's something different. So if you use this one to compute the standard error, then the standard error will be wrong. And if the standard error is wrong, then your confidence interval is no longer precise. And it will be written in this way. Yeah, so the variance covariance matrix will be written in the way it's x prime x to the minus 1, x prime omega x prime x to the minus 1, and omega here is the expectation of epsilon prime given x. Yeah. So how can we know that the error term is heteroscedastic? I have included a small explanation on what to do here. Yeah, so basically, you predict the value of sigma square, that is s square for si square for each observation after running the OLS model. Then you will regress the estimated sigma I square, or that actually the si squares on the explanatory variables, and test for the null hypothesis that all coefficients in the additional regression are 0 except the constant term. Okay, so in econometrics, to fix this problem, people has come up with an empirical variance covariance matrix, which is defined in this way. So variance b given x is computed in this way. Yeah. And if you want data to compute your heteroscedasticity robust variance covariance matrix, you only need to indicate at the end of your equation VCE robust. Then data will correct for it. Okay, let's see how we could do it. Can you please turn on the fan for me? Now, for heteroscedasticity, let's say we run the regression. Yeah, you get the result here. Now you need to type, this is the test of heteroscedasticity. Okay, I want to indicate the name here. Building command to test multi-collinearity. By the way, I received emails from you guys explaining why you could answer or why you could not answer certain questions from me during the class. That's fine. Okay, I just might want to make it a cordial, let's say a cordial classroom atmosphere. I don't want to criticize anyone. If you may answer correctly, you got some pluses. And if you do not answer it correctly, you may get a question mark or maybe a minus if you're absent. But that's in the end, to be honest, if I subtract points from you and you have lower grade, I will think twice. But I never think again if I have to if I have the opportunity to adjust your grades up. So don't worry. Yeah. So it's I mean this is just an opportunity to exchange, and don't worry if you cannot answer a question, that's fine. Now, when you want to test for heteroscedasticity, you just after running the regression, you just need to type a stat head test, and this is the result. This is what you would get. This is what you would get. So, what is our conclusion here? What is our conclusion in this case? I may ask someone. Let's see. Let's see. Hello Huỳnh Ánh Nhật. Hello Ánh Nhật, are you there?
Hello.
Okay, so how should we, what is our conclusion given the test result in our screen?
I think we
Should we conclude that the variable, the variants are homoscedastic, or should we reject the null?
I think we should reject the null.
The null is, so what is the alternative? What is the alternative then?
The alternative is
The alternative is okay. I may ask someone else. Now let's just stay focused. Anh Nhật. Now Nguyễn Hồng Thanh Ngân. Hello Thanh Ngân, are you there? Hello Thanh Ngân.
Can you hear me, sir?
Okay, I can hear you. So what is our conclusion now? Should we reject the null? Should we reject the null?
I think we
Be brave. Just express your opinion. Don't worry.
I think we should not reject the null hypothesis.
Okay, so what is the null hypothesis here, Ngân? What is the null hypothesis here? What is our null hypothesis here? The null hypothesis is, let me invite someone else. Okay, thank you. That's fine. Let's move on. Lưu Minh Thùy. Hello, Miss Lưu Minh Thùy.
Hello.
Okay, so what is our null hypothesis in this case, Minh Thùy?
I think based on the test result, if we reject the null, the probability of making a mistake is 0. So we should reject the null.
Okay, we should reject the null, right? That's it's a clear. No, I want to make it a clear mechanical answer. Okay, good. That's the first step. Now the next step I want to ask Minh Thùy is, Minh Thùy, what is the null hypothesis here?
Null hypothesis is a constant variance.
That's it. That is constant variance or homoscedasticity, right? Constant variance. They are the same. So we reject the null because we have to accept the fact that the variants are not constant. They vary from one variable to the next. Is that right, Minh Thùy?
Yes.
Okay, and that is if that is the case, then we will have to correct for it, right?
Yes.
We have to correct for it. And this is how we correct for it. Now, thank you, Minh Thủy. I will give you a class for that.
Thank you.
And I want to thank you too. I gave you a minus in the past. I don't know for what reason. When I invited, you were not there. I guess. But but I think you already got a 3. No, Lưu Minh Thủy. This is okay. You were not in the class on the 38th, right? Now, ladies and gentlemen. So thank you, Minh Thủy. And now we move on. Ladies and gentlemen, the heteroscedasticity test is actually first, you run a regression. You run the regression, then you pick the E hat. That is the residual, right? Then you generate the sigma square hat, that is equal to E hat square. So you create the SI square. That SI is actually the estimate of sigma I. Then you take the log of sigma square hat as this one, and you regress log of sigma hat on all of the explanatory variables. Then you test for their significance. And the result will not be exactly the same when you run the theta this way, but they are more or less the same. So you will get the same conclusion. Maybe the test value is a little bit different due to the Boolean function in theta. Yeah, but the idea is that you regress the square of the estimated error on the set of the independent variables. Okay. Yeah. Now I want to draw your attention to a new command, that is outrect2. Outrect2. Now, this might be the final step to get a beautiful paper. Yeah, a beautiful paper. So now we are going to the command outrect2. Outrect2. See? Outrect2. Now, can you please type into stata? Can you please type into stata? SSC install outrect2 replace. Okay. What do you get? What do you get, ladies and gentlemen? Tuấn is saying his data turns itself off. Sorry. Might be that the date in your system. The date in your system. But it should work. But if it doesn't work, it might be the case that you have not turned back your system date yet. No, but can you get the command installed, Miss Thanh Thủy?
My laptop is running out of battery, so I cannot run Stata. Otherwise, it would just crash. Sorry.
Okay, so you have not run it yet. Okay, Vũ Tính Bảo is saying my Stata Trịnh Minh Đức has also successfully installed it. Yeah. So hopefully, if you cannot install it, if you cannot install it, then please find some way to fix it in the next few days. Yeah. So this is the idea of Outtrack 2. This is the idea of Outtrack 2. So after you run a regression and you run the command Outtrack 2, you will get beautiful tables. The first, now you may study and you will see it. The first time I run the Outtrack 2 command, I will use the subcommand replace. So meaning that every time I run this command, it will erase all of the previously created table with the same name and create a new one. So, and then append means that every time you run an append command, it will append the estimate results into your table. So this is what I would get. I would get an XML file that gives me the coefficient, then the standard error, and you will see that this is not corrected for heteroscedasticity, and this is corrected for heteroscedasticity. And this is the table that I have created. And after some manipulation, like for example in view, I remove the I will home. I will remove the so I will delete the unnecessary rows. And for example, if I do not want to so I may add some more, besides this, I may add some more columns, and you will notice that I have, if I run this one a second time, a third time, right? A third time, and I open them up, you may see that I have a table that could be formatted into, for example, I can write it in this way. I will try to keep this, not to convert, but ignore the error. And then I would say this is model 1. This is model 2. This is model 3. This is model 4. See? Model 4. And then the variables, the coefficients are on the first line, and the 3 stars indicates that the coefficient is significant at 1% level. P is smaller than 0.01. 2 star means the coefficient is significant at 5% level, and 1 star indicates the coefficient is significant at 10% level. Down here in the bracket, you would get the standard error. The standard error. Yeah. So it will bring you to something like this one. So this is the newly written paper that from my own. and you will see that we have tables like this one. We have table like this one and like this one. Yeah. So the table are created by using the outrect2 command. So each time you run the model, you indicate to Stata the variables that you want the coefficient to be included, and with that, you would have your beautifully looking table. So this is the important thing to create your empirical results. Yeah. So I would draw attention to this handy command. Looking at this one, you may see that this model is corrected and this model is not corrected, right? So if I run it again, and for the sake of being clear, I will show you the results. Yeah. So in comparison with the model correcting for, if you correct for heteroscedasticity, you will see that the error term of the one that is corrected for heteroscedasticity is larger than the error term. That is, we use the wrong assumption. So in this case, this one is nothing more than following the x prime x to the minus 1 sigma square. Actually, s square. And s here is equal to summation of ei square divided by n minus k. This one is computed by using the model x prime x to the minus 1 x prime omega x prime x to the minus 1. Omega is the expectation of epsilon prime given x. Yeah, given x. This is the heteroscedasticity corrected variance and covariance matrix. So you may notice that the value of the coefficients are the same, but the standard error is larger. So when there exists the heteroscedasticity, the actual standard error is larger than the perfect model when the error terms nothing is perfect. The classical regression model when the homoscedasticity assumption is met. Yeah. So the difference is mainly in the way they compute the standard error. Good. So let's move on. Now we came to the last point, and then we are basically done with the course. Tomorrow will be practical modeling. Take a deep breath, saying, yeah, life is going to be beautiful again. Life is going to be beautiful again. So this is, we come to we have the autocorrelation problem at the end, but now we deal with the most difficult problem in econometrics. Yeah. The most difficult problem in econometrics. I will give you 10 minutes to open the slide and go through this part before I start lecturing. Please. You are given 10 minutes, not for a break, okay? You have to read the slides and make a picture of what I'm going to talk about, because it involves some abstract points that I need you to really understand. Yeah, so you have 9 minutes left. I will come back at 3:30 sharp, and I will keep speaking until 4, and then we are done. Yeah. I have been speaking to myself for some time. Okay, but that should be fine. Okay, now it only happens. I only recognize when I ask and no one answer. Okay, but that should be fine. Even if I turn on my microphone, no one answers, so it should be okay. It should be okay. Now, ladies and gentlemen, we are coming across maybe the last piece of knowledge that I want to include into this course. If you watch the videos that I have provided, there are some parts that have been left out from the course. But many people agree that if I include all of those topics into the course, it would make a semester-long master course. So let's say we live with what is necessary for now, and we should be practical. Even though I want you to know everything, I know, but in econometrics, I mean, but in the end, we may not have enough time. For now, let's consider assumption number 3 when it's violation. Yeah, assumption number 3 is that the error term, the expectation of epsilon given x. If you know x in conditional expectation terms, if you know x, you do not know anything about the realization of the error term. We cannot say anything about how large or small the realization of the error term is. The only thing we know is that it has a mean 0 and a variance sigma square. And with that, we want to be precise here. So in the instrumental regression problem, if y is equal to x beta plus epsilon, the assumptions are stated here. 1, 2, 4, 5, 6. All of the 5 assumptions, assumption 1, assumption 2, assumption 4, assumption 5, assumption 6 are assumed to be okay. We only want to focus on assumption 3, violation. That is to say, the expectation of epsilon given x is no longer a vector of 0. Some of the variables in x are correlated with the error term, and we call it the endogenous problem. And to solve this problem, we use the so-called instrumental variable regression solution. Okay, so it is the instrumental variable. Okay, now let me be more specific about this body of knowledge. So suppose that we are interested in a model that is y of x beta plus epsilon, y equal to x beta plus epsilon. And now we know that the expectation of epsilon given x is no longer 0. However, if we could find a set of instrument z which satisfy the condition expectation of epsilon given z is 0. Then the solution is, let's say, we may not be make in our analysis here, x includes a number of variables. Not all variables in x, but only some of the variables in x, say x2, are endogenous. So we can have the assumption that expectation of x2 times epsilon is not 0. How? So in order to make the problem explicit, we will split or we will partition the explanatory variables into two sets. One is the variable x1, that is, this one is exogenous. X1 is exogenous. Okay, the exogenous part, I want to make it clear, part. And the x2 includes all endogenous. Variables. Okay, this is how we make it. Suppose that we could find the number of instruments Z2 for X2. So X1, they are exogenous. They are exogenous. X1 are exogenous. So they are the instrument for themselves. The X2 are endogenous. So we need to find the number of instruments, let's call and put them into a set Z2. So Z2 is the instrument for X2. Then we form the new matrix Z, which is equal to X1 and Z2. X1 and Z2. Z2. Yeah. X1 and Z2. So because we have found that Z is assumed to be exogenous, the expectation of Z, so when we assume that Z to be exogenous, we mean that the expectation of epsilon given Z is 0. In other words, the correlation and the covariance between Z and epsilon is 0. So we define the new loss function G beta that is defined as equal to Z prime, the summation of Z prime, Zi prime, of Zi prime epsilon I, it is equal to Zi prime times Yi minus Xi beta. And then we take the first moment, that is to take the average of the Z of the G beta, that is equal to 1 over n times the summation of Gi beta from I equal 1 to n. Because the Z's are exogenous, the first moment of G, because this is exogenous, this one is 0, right? The first moment of G beta is 0. So this model, this approach to modeling is called the general methods of moment. So we use the sample to collect, to estimate the sample mean and impose a condition that the sample mean is equal to the population mean. And then with that, we can estimate the coefficients. Now let me be more specific. Let's define L to be the dimension of Z and K to be the dimension of X. If L is equal to X, to K, we are in the position of exact identify, meaning that, okay, you know that the expectation of Zi, epsilon I is given X is 0. Okay, so in or we can say the summation of Zi, the summation of Zi and Ei is 0, or we can say Z prime Y minus X Z prime E is 0. and that is nothing more than the condition here. So with that, we would have z prime times, it is similar to when in the case we have x prime y x prime e is 0. This is what we have in the ordinary least square. However, in this case, the x includes x1 and x2, and x2 are endogenous. We have to find the new instrument replacing the x2, and then we have the z matrix of instruments, right? Okay, of instruments. So multiply them out, you would have z prime y equal to z prime x beta, and z prime x beta is equal to z prime y, and the beta, the estimate using the general methods of moment is equal to z prime x to the minus 1 z prime y. So basically, you just replace the BOLS will be equal to x prime x to the minus 1 x prime y. So you replace the instrument, the endogenous part by the instruments. When there is no endogenous variable, z2 is equal to x2 and z is equal to x, the beta GMM is equal to the BGMM is the estimate using the general methods of moment is equal to the OLS estimate. So the OLS, that is the ordinary least square model that we have discussed so far, is just a special case of the general methods of moment. Okay. That is still very abstract. Because come on, you have the z, and where do you find the z, and how can you form these variables? This is the theory. In practice, it would be much more straightforward. So when L is larger than K, there are more equations than unknowns. Okay, when L is larger than K, there are more equations than unknowns. So our solution is, first you regress the x on z and get the predicted value. So x tilde is equal to z prime, z times z prime z to the minus 1 z prime x. It is equal to pz times x. By doing this regression, we only retain the exogenous part of x. The endogenous part mzx is removed by the first stage regression. Okay, then we will regress y on the x tilde and get the result. This procedure is known as a two-stage least squares. So the beta GMM is estimated as equal to x prime x, x tilde prime x tilde to the minus 1 x tilde prime y, and it is equal to x prime pz x to the minus 1 x prime pz y. Now, so because x prime pz y, you may notice here. So BGMM, the expectation of BGMM given x is equal to, now I want to write out, it is equal to x prime pz x to the minus 1 x prime pz. Now down here y I will replace it equal to x beta plus epsilon. Yeah, so it will be equal to x prime pz x to the minus 1 x prime pz x beta, correct, plus x prime pz x to the minus 1 x prime pz epsilon. Okay, now if you take the expectation, of beta's BGMM given z, it will be equal to beta plus the expectation of x prime pz x. Now, let's say I write down here. Okay, it is equal to x prime pz x x prime pz equal to x prime p. From down here, it will be equal to the x prime pz x to the minus 1 x prime pz x is the identity. It will be equal to beta plus the expectation of x prime pz x to the minus 1 x prime. Now pz now is written out. X prime z prime z to the minus 1 z prime epsilon. And because we assume z to be at the expectation, this one is 0 because the expectation of epsilon given z is 0. Right? It's 0. So in that way, the expectation of the beta general method of moment is equal to, this one is equal to the true value. Okay. So basically the idea is very simple. If the axes are endogenous, and we would regress the x on a set of instrument z, we only take the prediction or the projection of x on the z space. The z space is assumed to be orthogonal to the epsilon space. So in the end, the expectation of the beta GMM is equal to the true value. Okay. Now let's do that in theta. Come on, endogeneity. Now I want to load the data. So this is in this regression. We are interested in explaining how the IQ score, how intelligent you are, influences the wages and salary that you are paid. Okay. The problem with this is, do you think that is an interesting question? We talk a lot about IQ, people with high IQ. I know that all of you would have the IQ of 180 or higher. But let's say maybe VU students are all nerds. You just know how to study, but you don't know how to make money actually. Studying well, being smart might not mean that you will make a lot of money. Come on, that's the sad truth, right? Of course, if you are smart, you learn, you study at VU, you are better equipped with tools and strategies to win. But you must know how to turn the knowledge into your skills and your strength. Yeah. So let's say we may have a big debate, a big debate on who is if people with better IQ are better paid. Now, the problem with this regression is, now, ladies and gentlemen, so in this regression, you have, this is the LW. LW is the, now, I want to show you the meaning of the variables. Okay. I want to show you the meaning of the variables first. Yeah, the meaning of the variables first. So in this case, you would have the meaning of the variables. Uh-oh, this is not yet. I'm sorry. Now, let's say I have to load the data in, have I? Endogeneity. Uh-huh. Okay, so we have the labels of the variables in this way. Okay, so you have variable R and S as resident in the south. Mod is marital status if one is married. SMSA is resident in metro area. MET is mother's education. IQ is IQ score. Now KWW is a variable on the score on the knowledge in world of work test. So this is a test they came to your office and give you some tests and ask you to do quickly. Yeah. S is schooling year, completed years of schooling. X here is experience in years. Tenure is a tenure in years. What do I mean by tenure? How long you have worked for the current company? You may have a long experience of working, but you have been working for, let's say, after your graduation, you work for Goldman Sachs. After 30 years, you come back to Vietnam, and you work for the State Bank of Vietnam, and you work for 2 years. That your tenure is 2 years, but your experience is 32 years. Yeah, 32 years. So tenure and LW is a log of which, and then you have a number of dummies. Tomorrow we will talk a lot about dummies and similar things. Yeah, when you have the variable of 0, 1, that is a practical modeling issue. Now, so in this case, you want to explain how. Now, ladies and gentlemen, this is the key for you to understand the problem. You want to explain how IQ will influence your wages and salary. The problem is IQ is highly correlated with your IQ might be high, but it might not be, it might not reflect your ability. The IQ is just one variable explaining how capable you are in learning, in earning, right? So the IQ may be driven, both IQ and your wages and salary are actually driven by a factor that is plus something unknown here, unobservable, plus epsilon, something that you don't know. So when you put all the unobservable and the epsilon into the error term, this one, let's say U, this is the error term. So the expectation of the unobservable okay, given IQ is not 0. It is not 0 because, I'm sorry, IQ. not 0. So in this, if you have higher IQ, I may doubt that you are a very smart person. And if you are a smart person, you will know how to to play the game, and you will earn high anyhow. In this case, if you know, I know your IQ, I know that you will have a higher wage and salary. So on average, given your education, your residence area, if I know that you have a very high IQ, I will probably also know that you have high income. So my perception about your IQ will change my prediction about how different you are from the average. In that case, I know your IQ, I know the error term. I change my error term. Yeah, so we have to fix this problem. Yeah, to fix this problem. So the first step, now following the procedures here, the first step is to regress x on the z and get the predicted value. So in this case, the IQ here, this is my x1. These variables are assumed to be exogenous. Now, exogenous variables include these variables. Endogenous is IQ. So the first stage in the instrumental variables is to regress the exogenous variable, endogenous variable on all of the instruments. The instruments, the set of instruments include the new instruments. These are the instruments for IQ and the exogenous independent variable themselves. And if you regress this one, you will get the regression like this one. And you can test if the instruments are highly correlated with the IQ, and the test saying that the instruments are capable of explaining the IQ. Then you, in the second stage, you will predict IQ IV as x beta, xb, and you will regress the log of wages and salary on IQ plus the set of the explanatory variable like before, and you may see that the log of IQ is significant. Yeah, significant. There is a so-called Hausmann test for endogeneity. So the first stage is that you regress IQ on the set of exogenous variables and the instruments. You predict the residual, and you include the residual in the regression. If the residual is significant, then you may see that there is a problem of endogeneity. And in this case, you see that there is no longer the correlation between the error term and the explanatory variable. So let's say in data, you have the built-in regression. So if you run IV regress two-stage least square, and then you will see this is how you say it in data. This is the independent the dependent variable. These are the independent variable. This is the endogenous explanatory variable, and these are the explanatory variable. If you run that regression, you would get the same result. So let me just show you how can I run that. If I run that one, I would get the two-stage least square. So the first stage is to regress IQ on these variables. The second stage is to make the prediction, and you would get exactly the same result. Yeah. So basically, the instrumental approach is to decompose the endogenous explanatory variables into two parts. The part that is exogenous will be used again as the explanatory variable, and the part that is endogenous, that is correlated with the error term, will be thrown away. That's the idea, yeah. And with that, I think we are done with the part on. There is some discussion here I have included about testing for the whether we really need to do the instrumental variable, and it is called the Hausman ủ Watson Hausman test, and in data you can type it is that endogenous after running the IV request command. Okay, now so basically I say it again, when the assumption number 3 cannot be satisfied, the endogenous, the X are endogenous, meaning that if you know the X, you will know you change your prediction about the error term. Yeah, you change the prediction about the error term. So the first thing you need to do is to find a set of instrument variable. You regress the X that is endogenous on the Z and get the predicted value, and then you get the replace the predicted value into the regression. Now you can say I can show, you can see it here. First, you would love to run the regression. The thing is, what we are interested in running this equation. Right? We are interested in running this equation. However, LW. However, in this set of variables, we know that IQ is endogenous. If we know IQ, we will know the error term. So we have to fix for it. We find the instrument for IQ, that is the mother's education, and a score on the knowledge at work. So the idea here is that if your mother has very good education, you are more likely to be smart. Some gentlemen will be sad, but the truth is, how smart the children are depends strongly on how smart the mother is. So we are not to be blamed. Two sides. There are two sides of it. The one side, on the one hand, is if you have beautiful and smart children, that's the result of your wife's hard work. So if your children are happen, unluckily to be the black sheep in the family, that is also her fault. So we are, we are nonsense. We innocent. We do not bear any responsibility for that. So my father was very sad when I told him just the result of a study that how smart the children go depends on the mother. But come on, the idea is that I'm saying that because there is a reason behind why we choose our instrument. Our instrument are instruments. Are mother's education and the knowledge at work score. Yeah. So the first step is to you regress the endogenous variable on the set of exogenous variables and the instrument. Then you predict the value. So IQ, IV, that you predict you get the predicted value. You replace, instead of having IQ here, you replace it by the predicted value. That's the idea. And the results shown in this slide, following this approach, is again unbiased. So why is it so important to have an unbiased estimator? Because your estimation must be equal to the true value. If you run an equation and your estimate is, you do not know if it is equal to the true value or not, then we are in deep trouble. I don't know. I run a regression, I get a result, but I don't know if it is true. You know, that create a lot of questions about what we have done. So the nice thing here is I run a regression, I got a result. I know that I may have some sample error, sampling error, but the expectation of my estimate is equal to the true value. And in this case, our conclusion is that IQ score positively contribute to wages and salary. Yeah, to wages and salary. So with that, I will stop our class today. Tomorrow, I will send out a problem set, a very simple problem set to kind of for you to review what we have done. Very simple, but you all have to please do it. And tomorrow we will mainly talk about, if you are given a data set, how to combine them together and how to do the research empirically. Yeah. Okay. So thank you for your patience, and I look forward to seeing you tomorrow. Now I will, after the class, I will start checking the videos if they work or if they do not work. Yeah. So today it's very weird, and I will have to also to learn from WebEx on what happened when they only replace the video but not my screen. And I will check it out. But for today, I want to thank you for your patience, and I look forward to seeing you tomorrow. Yeah. Bye. Okay, some of you are suggesting on what to use to record. I will try. Yeah, thank you. Thank you you all, and goodbye.